Welcome! Our objective for this video is to determine the properties of our elements based on their electron configurations and their position on the periodic table. We spent a long time deciding how to picture our electrons in our atom. Now we want to use those skills to figure out the properties of our elements. As it turns out, many chemical properties are dictated only by what we call the valence electrons. These are our outermost electrons in an atom. We only have to care about these valence electrons because typically they're the ones that participate in chemical bonds and chemical reactions. To identify our valence electrons, at least for the main group elements, we can identify how many electrons are in the highest quantum number shell. The alternative to valence electrons are core electrons. These core electrons are held very tightly to our atom. They don't participate in bonding, and we're safe to ignore them for a lot of our purposes. We can start with an example. If you want to look at the electron configuration for a certain element, we can look at iodine. We can write the electron configuration here, starting with our noble gas above it, and then working our way over to get to the element that we care about. Whenever we use this noble gas abbreviation, the noble gas here, the electrons represented by that noble gas have to be core electrons. The outermost electrons are the ones in the highest shell. In this case, it's the n equals 5 shell. Here, the electrons in that 4 shell don't really count as valence, even though they're not in the noble gas bracket. We still get to count them as core electrons. If we add up the number of electrons in these outermost shell orbitals, we get a total of 2 plus 5. That is 7 valence electrons. 36 electrons from krypton and 10 more electrons in those d orbitals for a total of 46 electrons that count as core electrons. Once we start to write out these electron configurations for all of our elements, we can start to notice a pattern. Everything in group 1 has just a single valence electron. Everything in group 2 has 2 valence electrons. Everything in group 3, or I like to call it 13, in the main group, this periodic table is omitting the transition metals. Everything in group 13 has 3 valence electrons. In 14, we have 4 valence electrons, and so on, so forth, all the way up to 18, where we have 8 valence electrons in group 18. As we go down the periodic table, we have bigger orbitals, but we have similar electron configurations. The number of valence electrons is going to be the same within a column, and even better than that, the number of valence electrons is equal to our group number, or for that right-hand side, maybe that group number minus 10. We're going to utilize these patterns in our electron configurations to gain some insight into our properties of our atoms. As it turns out, quantum mechanics says that atoms with 8 valence electrons should be extra stable, even more so than you would normally think. This is predicted by calculations that we really don't have time to get into, but for us, we can jump right to that answer. 8 valence electrons is an extra stable amount of valence electrons. We can think of this as the octet rule. Atoms are trying to get 8 electrons around them, then they get to be even more stable, even more happy than you might otherwise expect. This helps us to predict the charges of our ions. We can try to gain or lose electrons until we have 8 valence electrons. This is going to correspond to the amount of electrons that noble gases have. Sodium has 1s electron as its final valence electron. If it can get rid of that electron and form a positive ion, now its outermost shell is empty. Its new valence shell underneath that will have that full 8, that full octet. Here's what this looks like written out. Sodium has this electron configuration 1s2, 2s2, 2p6, 3s1. If you form sodium plus, we get rid of that last electron, and now we have 8 valence electrons. That is a nice, happy octet. Because everything in group 1 has a very similar electron configuration, everything in group 1 should form a +1 ion. Likewise, in group 2, we have 2 valence electrons, which if we can get rid of them, we get to form a nice stable octet. Elements in group 2 like to form those +2 ions. Elements in group 17 have 5 valence electrons. They're looking to add 1 extra. When they do, they also can achieve that nice stable octet. Another property of our atoms that we want to consider is the atomic size. How big are these atoms? The size of our atoms has to depend on the electrons because, well, they're the ones that occupy the space in our atom. As you go down the periodic table, we get bigger orbitals. As these electrons get into bigger orbitals, the atom gets bigger. As we go to the right on the periodic table, we're adding extra protons into the nucleus, but we're not going to the next shell. So those extra protons in the nucleus get to pull our electrons in tighter. The result is that our biggest elements tend to be at the bottom left of the periodic table. Our smallest elements are at the top right of the periodic table. We can understand why this trend is true. And if we're just looking for a quick answer, we can compare two elements just based on their position on the periodic table. The next property that we can consider is ionization energy. This is the energy required to pull an electron away from an atom. Removing electrons is going to be harder to do the closer they are to the nucleus. Electrons that are close to the nucleus are held tightly and don't want to leave. Alternatively, if electrons are far away from the nucleus, they're going to be easier to pluck away. Because of this, the highest ionization energy is going to be when you go to the right and when you go up. Lastly, we can consider metallic character for our elements. Metals like to lose electrons during chemical reactions. Metallic character is going to be related to our ionization energy. The lower the ionization energy, the more metallic our element is. The trend for metallic character, therefore, has to be the opposite of our trend for ionization energy. As you go down, as you go to the left, that is where you have more metallic elements. We already kind of knew this. Our metals are below this zigzag line on the periodic table, to the bottom left of that line. Now we have some more intuition why that's the case. And we can compare any two elements to each other, which one is more metallic, which one is less metallic. We've made it to the end. By now we should determine the properties of our elements based on their electron configurations, and we can shortcut using the position on the periodic table. Well, there we go. Thanks so much for tuning in. Hope you all have a great day, and I will catch you next time.